Hello, this is Walter Leite. This is part 3 of uh, my videos about the code of chapter 7 of my book, Practical Propensity Score Methods Using R. Um, chapter 7 is about propensity score methods for continuous treatment doses. In this video, I will show you different ways to evaluate covariate balance. We'll be using propensity score weights. Those are inverse probability weights that were obtained in a previous video with different methods, such as a linear model, covariate balance propensity score, and Bayesian additive regression trees. So the first thing I will do here is load the data set. And you can find this code in the website practicalpropensityscore.com. Okay, so I'll load the data set. And I have here results from different methods. So I have the object that I obtained from running covariate balance propensity scores with the CBPS package, have the original data. I have a list of weights that I obtained from the EPW package, and I have objects that I obtained from the weighted package that I use to do estimation using kernel density, and also with Bayesian additive regression trees. Okay. So our first method to evaluate covariate balance will be a regression method. So first I'll create a vector of covariate names. So these are the covariates that we want to calculate covariate balance on. Some are binary, like charter school, magnet, those are binary. And then some, like number of students 2014, are continuous. But half of them are binary, half are continuous. So the first approach, I will use the survey package. Survey package is great for using weights, also for complex sampling designs. I will create two designs. One design with weights, which are the EPW weights. These are the first weights I obtained, which were based on the linear model for the treatment doses. And then I'll create a baseline survey design with no weights to see how bad covariate balance is without any adjustment for selection bias. I'll create an empty table. And then I will loop through all the variables in my covariate names vector. And for each variable, I will fit a regression with log is per examine as my dependent variable and the covariate as my independent variable. So there will be, it's bivariate regression, right? With just log is per examine and the covariate. And I will fit these regressions using the survey GLM package. Okay, so I will run the loop, which goes through all the covariates and calculates the bivariate regression of log is per examine on the covariate. And then I do that actually twice, one for using EPW weights and once for baseline with no weights. Then I just label the variables, variable coefficient baseline, coefficient EPW, add the covariate names, so embellishments to the table. And then I standardize by dividing by the standard deviation of log is per examine. So Here, it's important to remember that the continuous covariates were already standardized. They were z-scores. The binary covariates don't need to be standardized. So I obtain this table here, balance table PW, okay? And it shows how you can see covariate balance improved substantially. But if I'm using 0.1 as a cutoff, I still have some variables here that exceed that cutoff. Okay. So that's one method to evaluate covariate balance. Now, for the weights obtained with the covariate balance propensity score method, CBPS, the CBPS package has its own function to evaluate covariate balance. So what it does is calculates Pearson correlations between the continuous treatment assignment and each of the covariates, and it does that with and without weights. Okay, so for that, the function in the CBPS package is called balance. So I'll run that. And it returns a list. So all I do here is organize that list into a data frame and label. And let's take a look at the table we get. So you can see, based on the Pearson correlations with and without weight, the covariate balance with CBPS was excellent. The correlations dropped substantially. They're all very small. We can do a summary here to see, the maximum here was still very small. Now, there is a package specifically to evaluate covariate balance called Cobalt. It's an excellent package because it serves as a front end for evaluating covariate balance for most existing packages that do anything related to propensity scores for selection bias reduction. So I will use Cobalt to redo all what I did plus a few more methods. Okay, so I will load Cobalt here. And first, I'll use Cobalt to look at covariate balance with the PTW from the linear model. So this is the model here. And the weights are here. Now, I'll run this and it returns a list. So I'll just make it a data frame. And let's take a look. So the measure of covariate balance is also a correlation. So we have the correlation and adjustment that which doesn't show here, it's all NAs, and correlation adjusted for bias. And you can see the correlations. This is similar to the first table I showed. I used the regression, but the standardized regression coefficients for bivariate regression are correlations. The real difference here is it's the standardization methods between what I implemented first and what is done in the Cobalt package is a bit different. But yeah, you can see that here by this metric, only percent of free lunch didn't meet a criteria of 0.1. Now let's use Cobalt to look again at the covariate balance for CBPS. So it can do that. The code is very simple because it has a function specifically for CBPS. The nice thing about Cobalt function is that you can declare a threshold. Like here, I declare a threshold of 0.1, and it kind of makes the decision for you, is it balanced or not? Okay. Now, if you look at the covariate balance evaluated here and the covariate balance obtained from the CBPS package, it's a little bit different, but also similar. And the difference relates to how these correlations are calculated, like how the adjustment is applied. Note that the particularly with the binary variables, the values are quite different. So different, those are both correlations, but calculated in different ways. Now, we also use the Cobalt package for looking at the covariate balance for the weights we obtained with a linear model, but where the where kernel density estimation was used to obtain the generalized propensity scores. And you can see the covariate balance is really good. Shows always balance. Not as good as the one obtained with CBPS though. And then finally, we look at the covariate balance with the weights obtained with Bayesian additive regression trees, again using kernel density estimation for the generalized propensity score. Okay, and again, covariate balance is very good, but from all of these, the best covariate balance was obtained with the covariate balance propensity score. You can see these are the smallest numbers. And the worst covariate balance was with the using the linear model without kernel density estimation. So that's it in terms of covariate balance estimation. Again, you can find the code and the data sets in the website practicalpropensityscore.com.